Okay, this next one is involving a logarithm, but we still start the same way. So first things first, let's consider what's the domain. The domain in this case, well, x can be anything we want, but natural log of x is only defined for positive values. So that's going to restrict our domain to only positive values. Okay, so we find the first derivative, which is 1 minus 1 over x. If I try to write this as a single fraction, I want to get a common denominator. So I'm going to multiply this by x over x. So it's really x over x minus 1 over x, which is, of course, x minus 1 over x. So there's our derivative. We want to know where is the derivative either 0 or undefined. Where the numerator is equal to 0, that's where the whole derivative will be 0. So that's at x equals 1. And where the denominator is 0, that's where the where the derivative will be undefined. So we have a critical point where the derivative is 0 at 1, and a critical point where the derivative is undefined at 0. So we use our first derivative test, and we break up the number line into these intervals, and we test the derivative at these points. Now notice that my domain only includes values that are positive, so there's really no need to ever look at anything to the left of 0. So I'm really just left with what's happening between 0 and 1, and then again from 1 to infinity. So if you check the derivative, it's going to be negative on this interval and positive on this interval. So we know that the function is decreasing and then increasing. So I'm going from decreasing to increasing. I have a little local minimum at 1 comma something. And when I put 1 back into the original function, I get 1 minus the natural log of 1, which is 0. So 1 minus 0 is 1. Okay, now we do the same thing for the second derivative for concavity. The derivative of this is 0 minus the derivative of negative. So minus the derivative of 1 over x is minus the negative of 1 over x squared. So we get back to positive 1 over x squared. Hopefully you guys followed what I just said there. Certainly the numerator is never equal to 0, so it's just really where is the denominator equal to 0, and that's at 0. So for the second derivative, if we were thinking about it on our number line, we would really just be breaking it up by looking at values less than 0 and greater than 0. But again, the function's not defined for anything less than 0, so we're just picking the values after 0. And so pick any point really that's positive, and you will get a positive second derivative, which tells us that the curve is always concave up. We have no inflection points. If you try to find any x-intercepts, you'll see that you won't be able to find any because there's going to be no values of x that's equal to the natural log of x. If you need an explanation about that, think about that solving 0 equals x minus natural log of x is the same thing as solving where is natural log of x equal to x. But the function y equals x looks like that, and y equals natural log of x looks like that, and they never intersect. So that means this original function has no x-intercepts. Okay, so what's left to do? Let's plot the points. We have a local minimum at 1, 1. And then we've got nothing happening to the left of 0. And if we know anything about natural log of x, that makes sense because we have this sort of vertical asymptote happening here. And now we're decreasing until 1, and then increasing after that, but always concave up. So decreasing concave up, and then increasing concave up. Sorry, that's a little curvy. And if you wanted to verify that this doesn't somehow like flatten out, well, first of all, if it flattened out, you'd hit another local maximum. But if you just thought about the end behavior here, what's happening to this function as x grows large, certainly this whole thing is growing very large. So this is going off to infinity. And so that's the graph of that function.